Hi guys, today we're doing some more of the series and sequence stuff from sections 9, 4, and 9, 5. This video specifically is talking about infinite geometric series. And so let's get started. I don't want to do that, never mind. I'll just zoom in. Okay, so as I said, we're talking about infinite geometric series. Infinite means, yep, it goes on forever and forever. The list goes on forever. There's no end. So it means it's just going to keep going and going. Sometimes you can think of it like all even numbers that just keeps getting bigger and bigger. Sometimes you can think about like all of these fractions that are getting like smaller and smaller. So at the end of the day, it's just like a list that can go on and on forever. In this case, what we're looking for is we want our R to be between -1 and +1. And I'll kind of show you why that's important in a second. And the formula that we're going to use here is S sub n is equal to A sub 1 over 1 minus R. So I'm going to highlight that because we're going to reference this again. So again, this is for infinite series only. And it will be pretty explicit in the directions if it's an infinite series or if it's not. So don't let that concern you. So we're going to do some examples. So the first thing we're going to do is we're going to find the sum of the following infinite, that's not how you spell that, of the following infinite geometric series. So I'm going to give you a few terms and we're going to decide what's going on. So this first one will be 9 plus 3 plus 1 plus, and then I'm going to just do dot, dot, dot. That shows me that it goes on forever. That means that it's infinite. Okay, what is my R? It's a geometric, so we know that it's going to be R. It's not going to be D. My common ratio, what happens to get from 9 to 3? Yep, divide by 3. What happens to get from 3 to 1? Okay, divide by 3. And we're going to assume that that's a pattern that keeps on going. So my R, in this case, we don't write divides by 1. We write 1/3. That shows me the same thing. Okay, divide by 1/3. Remember this thing up here in between -1 and +1? This R that we're using, -1 is in between, or 1/3 is in between -1 and +1. So that's good. And this is what we call converge. If I asked, does it converge or diverge? Converge is where this is a true statement. So it falls into, or it's convergent because it's in between -1 and +1. But it's also because it goes towards a number, like it approaches one common number. When you get into like calculus, we'll talk about it having like a limit. Essentially, these converge because they have a limit, like they go up to one number and they don't really go past it. They essentially have a bound, they're bounded. Okay, so that being said, let's solve this guy. I'm just gonna do it underneath it. So we'll say S sub n equals A sub 1 was 9 over 1 minus R, which is 1/3. I like working horizontally with these fractions, but you can lay out your paper however you like. 1 minus 1/3 is going to be 2/3. 9 divided by 2/3 is the same thing as multiplying by the reciprocal. This becomes 9 over 1 times 3 over 2, and so I can make that 27 over 2, and that is my answer. That is my S of n. Cool, it's a sum of this series. If I was to find all of the numbers in that series, they would add up to this number. What happens is as they get smaller and smaller and smaller, they're going to approach this number. Like they're going to get closer and closer. So it might be like, what is 27 over 2? That's like 13.5, right? So it might be 13.499999. So it just gets closer and closer. All right. If you want to know more about that, let me know. But I think that's a basic enough understanding. The next series will be 0.25 plus -1.25 plus positive 6.25 plus blah, blah, blah. Okay, so first thing we got to figure out is, again, it's geometric. So what's my R? It's not what we're adding or subtracting, it's what we're multiplying or dividing to get to the next term. So to get from 0.25 to negative 1.25, oh, I don't know, that's the top of my head. Do you guys know that? To get from negative 1.25 to 6.25. You may know this off the top of your head, but I can't think of what happens right now for me. So what you can always do if you don't know, you can just divide like the second number by the first one and then the third one by the second one and see what the pattern is. So I can just do, whoa, negative 1.25 divided by 0.25 and see if that's going to be the same as what 6.25 divided by negative 1.25 is. And so if I throw that in my calculator because I don't know or I'm too tired to think about it, I can plug in my calculator and see that that's -5. Same thing for the next one, it's -5. So my R is -5. I'm timesing by -5 each time in order to get to the next number. So R equals -5. Okay, now, is -1 less than -5, which is less than 1? No, right? This part is the wrong part. Technically, this is true, but -5 is not in between those two numbers. So because of this, it diverges. It diverges because this is not a true statement. Just gonna put an X there to show that it's not true. But then also because it's diverging, it means that it doesn't just go to one number. It doesn't, I'm going to use the word approach. That's kind of a calculus word, but I think you guys can handle it. It doesn't go towards or it doesn't approach one number. If we were to find all of these up, it's not getting closer and closer to like 1 or closer and closer to 100. It's just going to keep getting bigger and bigger. And then also smaller and smaller because it's got a negative number in there too. Okay, so that's why it diverges. Divergent, I just also kind of mentioned this, but it happens when you increase or decrease without a bound. I talked about how convergent was bounded, divergent is not. So also when you increase / decrease without a bound. Okay. Let's, oh, we can't solve this, so this won't work because the R isn't true. So there is no S of n. When that happens, when it's not true, then I just don't have one. So we're going to keep moving on. Okay, so now we can also do this with not just like the first few terms, but we can also do this with sigma notation. So we're going to do some examples using sigma notation. And if you slept between now and the last time we did notes, sigma notation is that one with the E. So I'm going to have my E. I'm going to make it kind of big just so we can see it. My first example is going to have n equals 1 on the bottom, and the top is going to be infinity. This shows you that it's an infinite series because it has an actual infinity sign there. And then I'm going to have some expression next to it. So this expression is going to be 3 times 1/4 raised to the n minus 1. Okay? We know that we're starting with n equals 3. If I want to use the formula from above, I need a sub 1 and r. A sub 1 is whatever the first term in your sequence is. So if my n is 1, in order to find a sub 1, I'm just plugging 1 in for that n. So I'm going to do 3 times 1/4, 1 minus 1. You know 1 minus 1 is just 0. So anything raised to 0 is 1. So a sub 1 is 3. And then what's my r? This one's actually written really nicely because it's in an explicit formula. My R is at 1/4. That's kind of how we're changing it the rate each time. So now that I have those two things labeled, I'm going to do my S of n. I'll just do it next to it. S of n is equal to 3 over 1 minus 1/4. So let me change that. Slightly better. Okay. And so I'm going to start simplifying. I get 3 over 1 minus 1/4 is 3/4. And then 3 over 1 times reciprocal 4 over 3. My S of n here is 4. That worked out nicely. Let's do another one. Number 2. This one, I've got my E, it's infinity, but on this one, my N is going to equal 3 in the bottom. That's no worries. It just means when I find my A sub 1, my first term in here has an N of 3. So we're going to deal with that in a second. Here's the expression we're doing the sigma notation of, 2 times 1/3 raised to the N minus 1. So again, to find A sub 1, I'm doing it like the first term in here. And the first term in here uses N equals 3. So it's going to be 2 times 1/3 raised to the 3 minus 1. And we just have to use that. 2 times 1/3 squared. Don't forget we do our exponents before we do our multiplication. And those don't go together anyway. So raise your 1/3 to the second, 2 times 1/9. That becomes 2/9. Give you some order there. So that's your A sub 1 term. And then what's my R term here? Yep, just like last time, it's explicitly written. It's my 1/3. That's how we're changing each time. So now we're going to do our S sub n. So I'll do it right here. S sub n is equal to A sub 1, which in our case is 2/9. Just because it's a fraction, don't let that freak you out, over 1 minus R, which is 1/3. 1 minus 1/3 is going to be 2/3. And then I get to multiply those two together, multiply by the reciprocal. Oh, nice, I got some things to cancel out. The 2's cancel out, and then the 3, and then the 9 becomes a 3, so I'm left with 1/3. So if I were to list all of those terms, they would converge to go to 1/3, and that would be the sum. Okay. Oh, perfect. Let's go to the top of the page. I've got a quick little like rule for you essentially that kind of helps us keep things organized. If, I'll label this as a hint. Hint. If your N is going towards infinity, so like if you're in your sigma notation, we've got N equals infinity, and R is less than 1, then that means it's convergent. It's going to converge as a series. That's not how you spell that. Convergent. It's going to converge and you're going to be able to find the sum. If R is greater than 1, then it's divergent. And these are like in terms of like, is it a fraction or is it not a fraction? So like we used -5 earlier, but like 5, the like main part of it, that R part of it is bigger than 1. So that's why that counts. If it's a fraction, then it's less than 1 and it converges. Okay, one small little thing left is how to write repeating rational numbers as fractions. So like, let me write my little heading, how to write repeating. I'm going to write rational decimal. Ooh. As fractions. Okay, so let's see what that looks like. So an example is like if I have 0.13131313. Yes, there's a button in your calculator that you can do and make that into a fraction, but the best way is to think of it as a sum of infinite geometric series. So I can think of this as like a list. I can think of it like as 0.13 plus 0.0013 plus 0.000013 forever and forever. So essentially, if I were to add all of these up, they would equal that number. Okay, so my A1 here is pretty obvious. It's that 0.13 at the very beginning, so I can use that. I'm trying to think of this as a sum of infinite geometric series, so I can use a formula from right here. I need my A1 and my R. My R is what you multiply to get from, oh, that's not what I want, to get from here to here. Essentially, you're just moving the decimal, so we're multiplying by a decimal 0.01. If I multiply this by 0.01, it moves it 1, 2. It takes it from here, 1, 2, that way. So that's my R, this is my A sub 1, and so I'm going to plug that in to my little formula and use that. S of n equals 0.13 over 1 minus 0.01, 0.13 over 0.99, I think. And they're both decimals, so let's just make them whole numbers. Move that decimal 2 places, move that decimal 2 places. 13 over 99. If you don't believe me, throw in the calculator check. Let's try another one. This one is going to be 7.234234, etc., etc. Again, I'm going to see how this is a series. I've got 7 plus, the 7's not really part of the series. We're going to count everything else as part of the series, but they are going to be added together because at the end of the day, they're all one number. So I've got 0.234 plus 0.000234 plus etc. Again, I'm going to be multiplying by a decimal in order to move it. Since the one above it only had like 2 pieces that were repeating, I moved the decimal 2 places. This time I need to move it 3 places. So I've got 0.001. I'm going to use both 7 and I'm going to use 7 separately, and then my sum of my geometric sequence is going to be, or series is going to be a sub 1 is 0.234, and then I've got 1 minus my r, 0.001 on the bottom. 7's just being added to it because this is all one big number, but it's not part of the repeating, so I don't get to include it on top in that fraction. So I've got 7 plus 0.234 over 0.999. That becomes 7 plus 234 over 999. I can just move those decimal places. And then if you make 7 a fraction with 999 on the bottom, I think that becomes 6993. I can add that to the 234 over 999, and then I get one big fraction, which is 7227 over 999. Again, if you don't trust me, throw this in the calculator and see if it equals that. So that's fun, a way to think about rational numbers as fractions and decimals, and using our new concept. All right, check out the next video. It's going to be on explicit and recursive equations, and that's going to be your work for today. Have a great day, guys.